Welcome everyone to the third seminar of the series. It's a pleasure to have Professor Mengdi Wang from Princeton joining us virtually. She's going to talk about data efficient reinforcement learning in metric and feature space. The title is a little bit changed from the one we sent out, but she assures me that the theme stays the same. In terms of background, Professor Wang is an associate professor in the Department of Electrical Engineering and the Center for Statistics and Machine Learning at Princeton University. She's also affiliated with ORFE and Department of Computer Science. She got her PhD from MIT, and she has received a number of awards in her short career, which include the Young Researcher Prize in Continuous Optimization in 2016, the Princeton Seas Innovation Award, NSF Career Award, Google Faculty Award, MIT Tech Review 35 under 35 Innovation Award for China region. And she is involved in a number of professional activities, being associate editor and the area chair for various machine learning conferences. So it's a real pleasure to have her join us virtually, and I'll hand it over to her to tell us the exciting work that she has been doing. All yours, Mengdi. Thank you.
Hi, thank you, Wahid, for the very nice introduction. So, hello, everyone. So I decided to change the title of my talk like pretty last minute, because I gave this talk like a few days ago at a different venue, and people really like it. And then I thought maybe I could use this talk because the original title I gave was about a specific paper, about a specific analysis for a particular optimization problem. But I feel like it's actually nicer to switch to this more general talk to have an overview of interesting theoretical results in reinforcement learning. So I want to assure you that they're really about the same problem, except for like this one is like more general and slightly broader. Okay, so I'm going to talk about reinforcement learning, and I'm going to focus on reinforcement learning when we have structures in the learning problem. Okay, so when we have either metric or feature space. Okay, so I'm sure everyone heard about reinforcement learning. So reinforcement learning is just a fancy new name for Markov decision process, or at least the core problem in reinforcement learning is the classical Markov decision process. Okay, so let's just review notations. So in Markov decision process, the goal is to find a policy, so that maps every single state to an action or a distribution over actions. So we want to find a policy to maximize sum of rewards along a trajectory. And because there's randomness in the underlying linear process, we take expectation. So nowadays, in the community of reinforcement learning, we often call this tabular Markov decision process. So by tabular, we mean that usually we're implying that there is a finite set of states, and there's a finite set of actions to choose from at each state. And there's going to be reward function and transition probabilities, but those values might not be known in advance. And tabular really means that I have a bunch of states, but I don't know how the states relate to each other. I have no structural information in either the state space or the action space. Okay, in this case, this is usually known as a tabular MDP, no structural information. Okay, and then a very basic question in complexity theory is we care about the complexity for solving tabular Markov decision process. How does the sample complexity, the computational complexity, depends on the size of state and action spaces. Okay, so this is a collection of best known results for solving tabular MDP. So let's work with a sample and oracle. So we're going to suppose that we're given an oracle. So Sham Kakadi called it a generative model in his PhD thesis, meaning that I don't know the transition probability of the Markov decision process, but I have a generative model or a simulator that allows me to draw samples of random transitions from any given state S and action A. So here S and A are going to be chosen by us, but the simulator allows us to run the system by one-time step and generate a sample. Okay, and now a very basic question is, we want to ask, if this generative model is all we have to work with, then how many samples or how many queries do we need in order to estimate a near optimal policy? Okay, so that's the first very basic question. So in 2013, a few folks who are now with DeepMind, so they proved an information theoretical lower bound for the sample size. So they show that any estimator or any method needs at least this many, this many samples to find an absolute optimal policy with a meaningful probability. So if we look at this, so what do we care about in this sample size lower bound? So we have S times A, which is the total possible number of state and action pairs. So that is really controlling the dimension of the problem. Okay, and also the discount factor shows up in the sample size, controlling basically the effect of memory and dependence in the policy learning problem. And epsilon square is the policy error. So it turns out that even achieving this information threshold limit wasn't trivial. So there are many works trying to get upper bounds in this and that other way. And it was actually pretty recent that people could achieve the information theoretical limit. So, so this is one of the first paper where I participated, and there were other upper bounds following our paper. So basically, we did find one algorithm, and now there are multiple algorithms that could work with a generative model and is guaranteed to find an absolute optimal policy with a high probability. We can choose delta. And we can guarantee that the algorithm will success with this sample complexity, which nearly matches the information theoretical limit. And a related question is regret, which is I would say a question that is not exactly sample complexity, but rather about efficiency of online learning. And again, the regret of tabular MDP depends on square root of total number of state actions times t times cubic horizon. So I want to show you those basic results for the tabular case to really illustrate that even in the information limit, we cannot do better than S times A. Okay, the total number of states times the total number of actions controls the fundamental hardness of the problem. So we don't like this result at all, because S, which is the number of unique states, is usually a huge number. And everything could be exponential if we are working with a continuous system. And the number of policies could be even higher than the number of states. Okay, so when we have a really large S, the tight lower bound and upper bound are no longer meaningful, because the upper and lower bound, they are tight in the worst case sense, meaning that if we're working with a tabular problem without any structural information, the best and the worst we can get is going to depend on the dimension of the problem. But maybe there could be actual information that we can leverage to reduce the sample complexity upper and lower bounds. An even harder problem is, what if we want to learn to control a Markov decision process on the fly? So this setting is different from the generative model setting I just discussed. So when we have a generative model, essentially we're having a perfect simulator of the system. And then we can always decide to generate state transitions at places that we are not sure about. But in practice, say that we're actually trying to program in order to play a game, then our program might have to always start from the same initial state. So our algorithm is going to be playing the game over and over, but it cannot learn from a state unless it happens to visit that state. So then when we have this online learning problem, then things are actually becoming harder because the learning algorithm simply might not even be able to visit all states or visit all representative states in the state space. And also, every single algorithm can be viewed as a non-stationary policy. And the data we have generated are highly dependent, which creates additional challenge if we want to analyze what's happening theoretically. Okay. So in the online RL setting, so the simplest problem is known as the episodical reinforcement learning, in which the learning algorithm, usually we call it agent, the learning agent, interact with the environment episode by episode. And at the beginning of each episode, it always starts from the same initial state, okay, at 0 here. So in order to measure the efficiency of an online learning algorithm, we're going to measure its regret. So suppose that the learning algorithm has run for t time steps, where t is the number of episodes, n, times the horizon of each episode. Okay, so regret at time t is going to be the regret accumulated throughout n episodes. So we're going to calculate regret by comparing the optimal value that the optimal algorithm, the optimal policy would earn with the actual sum of rewards earned by our algorithm. So basically at each episode, the algorithm does a bunch of things and collect a reward. And we calculate the sum of rewards from generated by the algorithm and compare it with the optimal expected rewards. And we take sum of this difference. And that is the regret of an algorithm. So this can be viewed as a generalization of regret in bandit learning to reinforcement learning. And the problem is more challenging than bandit because we have a lot of dependence and we have to care more about the exploitation trade-off. Okay. So let's try to solve the problem. So let's add a little bit of structural information. So the first structural information we are going to have is, okay, I need something to help me generalize knowledge. Generalized knowledge means that my problem cannot be tabular. So if I have state A, so we have observations about state A, I want those observations to be telling me something about another state B. In the tabular case, A has nothing to do with B, and what I learn about A has nothing to do with B. In that case, the problem was harder. But now we have something to relate A and B. So the first basic structural knowledge we're going to work with is continuity. So we're going to simplify the problem and assume that this is really just a deterministic state transition system, deterministic control. And the only structural knowledge we have is we have a metric in the joint state action space. So some metric that measuring the distance, the similarity between one state and action pair and another state and action pair. And we're going to assume that all the unknown Q functions and the unknown transition functions are Lipschitz continuous with respect to this metric. Okay, so this is, we're only assuming continuity with respect to a particular metric. And now we have an algorithm. So recall that we have a learning algorithm which is going to be constantly updating its policies as it collects data. So at the beginning of a new episode, suppose that all the experiences has been stored in a buffer. So the algorithm has already made a bunch of decisions in the previous episode, and all that data is memorized. So now in the new episode, my agent is going to be calculating estimates of Q functions. And of course, we never know the transition function exactly, but we are going to estimate an upper bound of all the Q values by doing nearest neighbor search using data in the buffer right here. And the exact formula is this. So we want to be optimistic in the sense that if I observe a transition from a nearby state, I'm going to be adding a bonus proportional to the distance between this state and the current state I'm trying to estimate. Because I know that a nearby state doesn't give me exact estimate of value at the current state. So I'm going to calculate an upper bound by adding a bonus term. So every single sample in my data gives me an upper bound of my Q value update, okay? And I'm going to find the smallest upper bound from all the data. So this is really a combination between nearest neighbor search with optimistic Q update. So by doing so, we're able to calculate an upper bound for every single Q value based on the data we have, okay? And then we're going to use all the Q values we calculated greedily in the next episode. So that's a full algorithm. So at every new beginning, we look at the data we have, and we use the data to calculate the best upper bounds for all the Q values. And we're going to use our estimated Q values to find the next policy. And of course, in the next round, I'm going to use my new policy and I'm going to collect new data. But hopefully, this algorithm is already making striking a good balance between exploration and exploitation. Okay, so what can we prove? So we were actually able to prove a nice regret upper bound for this nearest neighbor MatrixRL algorithm. And we can show that, so K is the number of episodes. The regret upper bound depends on a polynomial function of diameter. I think L is the Lipschitz constant, and K is the episode. Okay, and also horizon. So, so here, this little d in the exponent is the doubling dimension of the state action space. And this big D is the diameter of the space with respect to the metric. Okay, so this proof is actually can be done in like one page. It's actually a pretty intuitive proof by combining dynamic programming together with nearest neighbor search. Okay, and we can also show that this regret bound is actually minimax optimal in the sense that there are problems that are fundamentally hard enough so that no algorithm can do better than this regret bound. Okay, so what's interesting here is the little d, which showed up in the regret bound, is the doubling dimension. So the doubling dimension, by definition, means that, okay, so I have a set of points, right? And then I'm going to find the smallest integer, k, such that every unit ball, every ball in the metric space can be covered by 2 to the power of k balls of half radius. All the radius are measured in the metric. So why is this interesting? So this is interesting because, for example, if my data lives in a lower dimensional manifold, say that my raw data could be just raw pixel images, But the raw pixel images are usually generated by a program using fewer parameters. And in that case, the space of images is going to form a smooth manifold. And the doubling dimension is going to be the smallest intrinsic dimension of the manifold. It is not the raw dimension of the raw image. So in some sense, this algorithm is doing manifold learning to simultaneously when solving the dynamic program. And its learning efficiency is determined by the fundamental doubling dimension of the state space rather than the pure dimension. Okay, so that's what we can do with a little bit of metric.
Mengdi, if I may ask a quick question. So here we are assuming that we know the reward function on all the state and action pairs, because in the upper bound.
No, we don't know. We only observe a reward whenever we visit that.
I see. But in the formula for the Q update, you have a minimization over R, right? So you use a
yeah. So this S prime and A prime, they are what we have observed before. So this R is part of my data buffer.
I see. So it's not over all SA, it's more like what we had in the past.
Yeah, it's over the experiences we have in the past. Exactly.
Okay, thank you.
Thank you. Okay, so that's what we can do with a little bit of metric continuity. So next, we hope to do better. So we're going to add more structures. So metric doesn't tell me too much. So now we're going to work with a feature map. So suppose that we have a state feature map, meaning that every single raw state can be mapped to a vector. And the dimensional vector is the dimensional feature space. So for example, like almost 30 years ago, researchers at that time can already solve the game of Tetris using handcrafted features. And turns out that only 22 features was enough to get human-like performance. So that is way earlier than the deep reinforcement learning age. Okay. So the reason to use feature is, so fundamentally, we are trying to present unknown functions in the high dimensional space by using fewer parameters. So in any dynamic programming algorithm, usually we need to calculate or estimate some value function of some policy. And the value function is going to be a function that is taking input some state. But the complexity of value function is really the complexity, the size of the state space. Okay. So now, if we have a good feature map, we are attempted to represent this value function, or in the discrete space, is a large value vector. We are attempted to represent the value using a linear model. So this vector, which could be of dimension S, can now be represented using a parameter vector in dimension n, with n being the number of feature functions. Okay, so that's really the motivation. And we can even generalize this to Hilbert space. Actually, sorry, this slide doesn't need Hilbert space. So for example, if we can further generalize this to, like, if we have feature representation to state action pairs and states, okay? And having good features essentially means that we can embed the unknown transition kernel into the feature space. So the unknown transition kernel is going to be, it could correspond to an infinite dimensional operator, but we can actually either approximate it or just embed it into a finite dimensional matrix through the feature map. So that's the basic idea. So this particular matrix embedding model allows us to learn the optimal policy way faster. Okay, so right now let's just think about this as really just as a parameterized model for the unknown transition kernel. Okay, so this unknown P, this probability density from state action to state, which we do not know, can be embedded or described by a matrix M, because we are mapping the space of states onto the space of finite dimensional features. Okay, so now let's try to solve RL.
Excuse me, can I ask a question?
Yeah, please.
So how is this Hilbert space embedding is different from deep reinforcement learning? Because there also you're trying to map the Q function to some kind of feature space.
Yeah, very good. This is just a theoretical abstraction of parameterized reinforcement learning. So we can think about deep learning as a particular parameterization. And here I'm talking about a very basic linear parameterization. Does that make sense?
Yeah, thank you.
Okay, thank you, great question. Okay, so say that we have this matrix model, then what do we do? So again, at the beginning of new episode, we have a bunch of samples collected so far. So this is the collection of state action states that we have observed in our experience. We are going to map each transition onto two feature vectors. Okay, and now in order to estimate the unknown transition kernel, this can be reduced to a matrix estimation problem, actually a matrix regression problem. So very simple. We just try to fit the unknown model or parameters of the unknown model onto the data we have so far. Okay, I think my math equations are actually too complicated, more complicated than necessary. It's really about we're fitting our transition model onto our data. And now the key is the following. We're not happy with a point estimate of my model parameter. Okay, we actually want to have a confidence ball around our model parameter. And in the matrix linear model case, we can construct a confidence set like this. Okay. And again, we're going to use this confidence set to do optimistic estimates. So now whenever we estimate Q values, I'm going to estimate Q values by picking the most optimistic matrix M in my confidence ball. In other words, we have a confidence set of estimated transition probability densities. We're picking the most optimistic model from the current confidence set, because we really want to have an upper bound of Q values. Okay, so we do this calculation and we find a bunch of Q values, which are the sharpest upper Q value estimates we could have based on the data we have. And then we use those Q values greedily in the next round to collect new data. So this is really very similar in spirit with the nearest neighbor search. The only difference is that algorithm calculates upper bounds by using nearest neighbors and continuity. And this update calculates Q upper bounds by constructing confidence ball based on the probability model. Okay, so what can we prove? We were able to show that, so if my unknown underlying dynamics can be fully embedded in the feature space, then the regret of the algorithm, which we call MatrixRL, because it's iterating over matrix. So this MatrixRL algorithm has a nice regret that is bounded by square root of t times dimension of the feature space times horizon square. So recall that if we don't have feature space, if we are working with a tabular setting, this regret depends polynomially on the total number of states. And now with this feature map, our regret depends linearly on dimension of feature map. So that's a huge reduction in regret, because we are using a lot of information to generalize knowledge from experiences to new states. Okay, and so this regret.
Sorry to interrupt again. So here, how do you choose the confidence ball, BN? I think you may need to choose it in a specific way, right? To
Oh, like, we just choose the best confidence ball by using our knowledge from regression.
I see.
So yeah, and
so
this is like okay.
Sorry. So basically, choice of beta n is critical for the optimality, I assume, right? So you need to choose it in
the choice of beta is so we have to choose some probability delta for failure, and then we calculate what's the right value of beta. But beta is roughly like a constant over number of data points.
Okay.
So we don't do a lot of maneuver there. But this is basically the best confidence set we can construct by using linear regression models.
Okay, thank you.
Thank you.
Can I also ask a question here?
Please.
So your upper bound and regret here increases quadratically with h, right? And h is your horizon, the length of an episode, right?
Yes.
Okay, so basically, if we have shorter episodes, this upper bound is smaller, right? Variability.
Yes.
Right? But if the length of an episode is too small, right? Then that episode may not be too informative in the sense that we are not really getting to see where we end up, right? If the length of episode is small. So how
that's a very good comment. So I think two answers. So first, indeed, the higher the larger h is, the higher the regret. So if we are learning to plan in a long horizon problem, then this is a harder problem, right? But if h is very small, like we take h equaling 1, then we might not really visit a lot of states, right? Yes. But however, when h is small, the problem reduces to a multi-embedded problem. So basically, we might not care so much about what happens afterwards because we only care about the rewards collected in the first time step. Does that make sense? So if h equals 1, this actually becomes a simpler problem. So although we are not learning about what happens after, but what happens after doesn't affect our performance.
All right, so it's fundamentally an easier problem. So
yes.
All right, thank you.
But you're right, like this dependence on h is tricky, and this dependence, I'm sure, is not optimal, but we cannot, actually, I don't know how to improve it by using a trivial argument. Okay, so next, the previous analysis is based on finite dimensional feature map. So you can imagine that everything we can do with feature map can generalize to a reproducing a kernel Hilbert space. So if we're giving a kernel function rather than a finite dimensional feature, a lot of the master analysis still goes through. Although the algorithm will look more complicated, but we don't have to look at the algorithm. So in that case, if we work with kernel space rather than feature map, then the regret, again, depends on a particular notion of effective dimension, which is this d tilde. And also something like the Hilbert space norm of the unknown transition kernel will show up. So this is really just a bunch of derivation from finite dimensional case to kernel space. Okay. Next, so I talk about if we have features and then we have a linear model, then we can learn with a provable regret. But what if we don't have a lot of prior knowledge to begin with? Okay, what if we don't have a linear model? So we were motivated from this recent paper by DeMine, which is called this MuZero paper. So they developed a new deep RL algorithm, which is supposed to be better than AlphaGo, AlphaZero, and all the other algorithms developed by DeMine. So the nice thing is MuZero is a single algorithm that can learn to solve a bunch of games, including chess, including Go, and including all the Atari games. So what's interesting, we know that AlphaZero is already very good in solving the game of Go, right? But AlphaZero was designed tailored to two-person zero-sum stochastic game. But there are many other games, like those video games. They are one-player games, and they have other special structures. So now the nice thing about MuZero is it's a single algorithm. So it's not designed tailored to a particular game, but it can actually solve all these games well enough and beat the best player in each. So the nice thing about MuZero is it tries to learn the rule of the game as it plays. And it does end-to-end training in the sense that it only tries to predict quantities that matter to the game, like values and policies. So what do I mean here is, like, for example, if we try to solve an Atari game, which is like a video game. So one could say, hey, what if we train a simulator to predict the next state of the game? And then we use this prediction to do planning, right? But if we want to predict the next state in this Atari game, it's going to be a raw pixel image. And then training an agent to predict an image actually is very computationally expensive. Okay, and we don't want our learning algorithm to predict information, to predict pixels that do not matter much for the optimal policy. So MuZero is really trying to not predict raw pixel image, not predict raw state, but only predict value and policies. So that's the main idea. So we adopt this idea to develop an abstract RL algorithm. Okay, so let me explain. Let me try to explain. So instead of trying to predict the next state or some known feature values at the next state, okay, we are going to run regression to predict this v hat value at next state. So the real key to this algorithm is this step, value-targeted regression. So we can imagine theta as parameter of our neural network. So we're using this neural network to predict value of the given state and the given action. So theta is the function class we're working with. So theta parameterized the function class we're working with. Okay, we're going to train theta by predicting value functions. And again, we're going to be constructing confidence set around the theta based on all the data we have. And then based on confidence set, we are going to be compute upper bounds for values and Q values. And we're going to use those values to calculate policies greedily. So this is really a more abstract framework of the online RL algorithm I just described. But what's really unintuitive is, so originally we were trying to estimate some parameter of the model to predict features of the next state, which is a very reasonable regression problem or a very reasonable prediction task. But now we're trying to find theta to predict v hat at next state. But v hat is a quantity that is being calculated and updated by the same algorithm. So this is very unintuitive. So the algorithm is estimating all the values, and the algorithm is trying to fit a state-to-state predictor to predict those values. But those values are actually changing. The values could be very off at the very beginning. And the algorithm changes the target value functions as it learns. And the target value functions changes our estimate of the transition function. So this is unintuitive, but in some way it is exactly what MuZero was doing. Okay. So this is what we could prove. So we were able to prove that as long as we know that my underlying dynamics can be parameterized by theta, meaning that the neural network parameter by theta is good enough for predicting values that we care about. So under that assumption, we were able to bound the regret of this learning algorithm by this by an upper bound, and the upper bound depends on a notion of eluder dimension of the function class parameterized by theta that we're working with. So we can think about this as a generalization of dimension to a nonlinear function class. If we work with features and linear model, that was just the dimension of the feature map. But now if we work with a neural network or a more general parameterized function class, then it's a particular notion called the eluder dimension of the function class. Okay, and this result will also give us the same d square root of t regret if we apply it to the special case of linear matrix models. So the real interesting message is it's actually okay to learn to predict these changing value functions. And the algorithm won't actually get stuck by calculating its own value function and using the same value functions to guide the learning process. So I think that's really the mysterious and the interesting part of this analysis. Okay.
Can I ask a question?
Mm-hmm. Yeah, please.
So this message that you mentioned wasn't already known in deep Q learning work where they estimate Q function and they get better and better as they go, but they use the same thing to act like epsilon greedily.
Yeah, a very good question. So I think people know that Q function and value functions are central to RL, but how to make it work and how to get provable regret was never known before. And also, this algorithm doesn't use epsilon greedy. Epsilon greedy is a particular way to encourage exploration. But here, exploration is encouraged by being optimistic within the confidence set. So the confidence set is actually important because it quantifies what we know and what we don't know about the underlying dynamics. And now, instead of being epsilon greedy at every state, we're actually trying to find the best exploration policy, taking account of all the uncertainties and doing a bunch of calculation. So that's the key step, optimistic planning. And that's where we need this, that's why we need the confidence set.
So this is basically, instead of learning the Q function, we are learning the value function. And instead of being epsilon greedy, we are doing this optimistic policy, right?
Yes, this optimistic planning, I think in the bandit case, this was really just upper confidence bandit. Yeah. Even in the bandit case, we don't want to do epsilon greedy exploration because we might be wasting a lot of time at suboptimal actions, right? So we want to really testing actions that have a good chance of being the optimal. And then the sampling distribution should adapt as our knowledge accumulates. And to put it rigorously, it means that we're calculating our confidence set and we're trying to do the best we can by looking at all possibilities from the confidence set.
I guess I have a question maybe on the next slide, or this slide and the next slide. So your order bound on doesn't involve beta. So how do you choose beta, the diameter of this? Because it's not in the O tilde, so I wasn't sure if there's a dependence on the.
No, there's no dependence. There's a particular choice of beta.
Okay, so there's a choice.
Yeah,
okay.
I forgot. It could take a particular form for this abstract theorem. I think in the earlier case, it was really just some constant over square root of n.
Oh, okay. So you don't need to have any knowledge of anything else to set beta.
Well,
you don't. I mean, you just need root n.
We need this. We need to choose beta using this delta.
Okay,
so
sure.
Some log 1 over delta in the beta. So if we want this regret to be bounded with a very high probability, then we might want to choose beta like in a more relaxed way to make sure that we are bounding it with high probability.
Okay, thank you.
Okay, thank you. Okay, so I don't have much time left. So I would just want, yeah, I will just explain one, okay, I'll skip this part. Okay, I will just explain like one application that we used to work on, and I thought it's interesting to share. So we try to apply RL, actually not online RL, but batch RL to a clinical optimization problem. So this problem is about the knee replacement procedure, not really the procedure, the episodes, the episodic treatment of knee replacement. So I have a friend who got his knee replaced and he really liked them. He told me that knee replacement is a very common surgical process to really make a person happy if he has a knee problem from his youngs. So we were looking at this problem because the Medicare started a few years ago, started a new payment policy. It used to be that the knee replacement was 100% covered by the Medicare, but now they decided that knee replacement is too costly and they will only cover knee replacement up to a limit. And then we got this question from an insurance company. So they share with us a bunch of clinical records and claims records saying that, can you guys like look at the data and see if the cost can be reduced in knee replacement, assuming that they can assign doctors and rehab centers in a more reasonable way. So we thought about this and we formulated into a Markov decision process. So we didn't have too many data. I think we have like 200 episodes, which was actually considered a big data set in the knee replacement literature. So for that data set, we're asking the question is, can we learn an optimal clinical decision policy? Which is, I think it wasn't possible because we don't have, the data is really not too big. So we cannot use that limited data to learn precisely how to prescribe clinical decisions at each possible state. We have too many states and too few data points. Okay, but however, we formulate this into a lower dimensional problem. We call it an intelligence crowdsourcing problem. So we're not going to be trying to learn how to prescribe each decision, each time point, but we're trying to put together all the clinicians who made decisions in my data set to say, hey, if we combine the best practice of this expert with the best expertise of the other expert, can we predict by putting those people together what will be a super expert, what will be the performance of a super expert? So we think about this as some sort of like imitation learning with policy optimization. And again, so we try to set this up as a Markov decision problem, which has a huge number of states. But we had another method which we developed, which is in some way similar to high-dimensional compressive sensing, but it's about compressing state space to preserve useful features. So we've applied that method to the data set to really compress the large state space into only a few features. Okay. And then we did in-sample test, out-sample test, cross-validation, simulation, a bunch of things. So in the end, we conclude that it's actually possible to put together best practices of the clinicians. And if we could do that, one could actually reduce the cost per episode by 1,000 USD without compromising the outcomes of the knee replacement. So that's actually, that isn't a big improvement for a single episode, but if we multiply this number by the total number of cases across US, that could be a huge savings. And we can further predict the probability distributions of different clinical pathways for a given patient under the recommended optimal policy. Okay, so in the end, I think theoretically speaking, it's possible to leverage structural information at a metric or feature space to make reinforcement learning more data efficient. And in practice, I think people are attempting to use techniques from high-dimensional statistics, high-dimensional machine learning, and compressive sensing to actually reduce dimensional feature space to make RL more practical and more data efficient in practically hard problems. So that's the end of my talk. Thank you very much.
Thank you so much, Mengdi. We'll give a virtual round of applause for this wonderful talk. So we already some questions were asked, but probably there are other lingering questions. Anyone, please jump in and ask.
I may have a quick question, if possible. So Mengdi here in the value function, if I replace the expectation with a risk measure, just to have more control of the actions, can I do it easily in your algorithms?
Not in my algorithm. I think getting regret upper bounds for risk neutral MDP is a non-trivial problem. But adding risk measure, so actually that's the talk which I proposed to give, but I didn't give. So there's this other talk which is really strongly related to risk measures. But I think how to learn with regret with risk measure, I think that's a wild open question, because even the definition of regret is no longer valid when we have risk measure. So what do we mean by regret if we care about risk measure? It's not clear. That's wild open. It's a very good topic for potential future research.
Okay, thank you. Thank you.
Thank you.
Other questions? So while people think about it, I had a quick question where you had to skip over because of time, but could you just briefly talk about how to choose features?
Okay, so I think I had something probably Wahid will be familiar with. So I was trying to actually apply some form of functional singular value decomposition to the unknown transition kernel. And the unknown transition kernel is infinitely dimensional, right? So we cannot do that. So I'm trying to do that decomposition in the kernel space. I think that's a very common idea. And in practice, so this is how to make it work in practice. Okay, let me remove the teasing plot. So the input is going to be my raw pixel image. So say that we are running DQN or any neural network. So I'm not going to use this to solve the RL problem. I'm going to use the neural network as an initial representation of state. And then we can play with this. For example, we can apply a composition between the neural network kernel and some Gaussian kernel, or just anything we feel is reasonable. So we lift the dimension of the state space onto a higher dimensional state space. And then we apply some form of low rank optimization. So that's one way, and that we can actually prove that after this, we are going to be able to map a raw pixel image into a feature vector with a few dimensions. And then this feature vector is going to be preserving the diffusion distance in the original dynamical process. So I'm not giving the proof here, but so this process is actually rigorous. We are preserving some notion of diffusion distance, quantifying similarity between states. And then we can apply this. And I didn't show this, but we actually apply this method to an Atari game. And we could actually compress the state space into pretty meaningful, I would say, meta states that are strategically meaningful.
Great, thank you.
Thank you.
Any other lingering questions?
So I have a question. In your nearest neighbor method, you have a bunch of data, right? And then based on some distance metric, you're trying to find some candidates for a given state action pair.
Right.
And then you perform updates, right? So do you make any assumptions on this on the like structure of data set that you have? Because I guess the efficiency of your algorithm depends on how rich your data set is in terms of like having these neighbors, right?
Yeah,
candidates.
Yeah, very good question. So in batch learning, in statistical learning, if we work with a batch data, then our quality of prediction depends on whether the data is well conditioned or not, right? Whether the data represent the state space. But in online RL, actually the data is generated by the same single algorithm. So the algorithm is actually designed in a way to be adaptive. Does that make sense? Again, I think a nice example will be in multi-embedded. The algorithm will start trying all actions with equal probability, but as it collects data, it's going to be focusing more and more on actions corresponding to potential high values, but also high uncertainties. So the algorithm is actually adapted in a sense to always try to collect the most informative data. And the same intuition applies here, because as long as we're trying to calculate optimistic upper bounds, then how sharp the upper bound actually depends on how close the neighbors are to this particular state and action point. So if all my neighbors are far away, then the upper bounds are going to be a very large upper bound. And then we are going to get a high Q value at this action that will encourage a greedy policy to try this action. So the algorithm is actually has this built-in adaptivity to try to collect data to learn better.
Okay. Makes sense.
Yeah, thank you.
Well, thank you.
Thank you.
In the interest of time, since she has a meeting in about 5 minutes, we'll conclude here. Thank you so much, Mengdi, and we'll leave you with another appreciation of you coming and joining us. So a virtual round of applause again.
Thank you very much. It's my pleasure.
Okay, thank you so much. And we have a new seminar next week with Professor Sovrit Sarah, and we'll see you there then.